our speaker, Dr. Georgia Tomova from the University of Leeds and the Leeds Institute for Data Analytics. She is a researcher who got her start in nutrition before transitioning into health data analytics, and then did her PhD, much of which I think she'll talk to you about in some detail today. She's also an excellent lecturer, so I think you're in for a treat. She teaches in the Introduction to Causal Inference course for health and social scientists, which is quite well known, based out of Leeds as well. And she co-leads the Alan Turing Institute Causal Inference Interest Group. So doing a lot of things for the community. We appreciate that. Without further ado, I'll hand it over to Georgia, and then we'll come back and have a Q&A at the end, which won't be recorded. Enjoy.
Can you hear me well at the back? Let me know if at any point you don't. Thank you for the introduction, Jess. It's a real pleasure to be in Berlin. This is my first time ever in Berlin. So thank you for the invitation. I'm really happy to be here. So today I'm going to talk about compositional data and how we can understand compositional data, both with fixed and variable totals, using DAGs and data simulations. And although I have data simulations in the title, I'll try and keep the talk focused on the conceptual level and use the simulations to support demonstrating some of the concepts, but I wouldn't be kind of delving into a lot of technical details. At the moment, in the last year, I've been working as a research fellow at the University of Leeds in the UK, and I've been focused on working with consumer purchase data to evaluate the impact of different interventions, both randomized and not, different health and sustainability related interventions. And I have general research interests in methods for epidemiology and with particular focus on causal inference. And before my current postdoc, I completed a PhD in epidemiology, which was again at the University of Leeds, but also jointly at the Alan Turing Institute in the UK. And my thesis was focused on addressing different compositional data challenges in dietary and physical activity data. And essentially what I'm going to be presenting today is part of my thesis. And Jess also mentioned that I co-lead the Alan Turing Institute Causal Inference Interest Group, so very much passionate about causal inference. So before I properly start to introduce compositional data, I'd like to pose a few different questions that at first glance might be completely unrelated. For example, in nutritional epidemiology, should we adjust for energy intake? This is a common challenge and a common question. In physical activity, how would we go about estimating the effect of, for example, swapping 15 minutes a day of sedentary time for 15 minutes of physical activity? In the context of climate impact, if we had to choose one, for example, would it be more effective to focus on shifting towards renewable resources, or would it be more effective to focus on trying to decrease the overall consumption overall? And then slightly more methodological rather than an applied question. Is it more appropriate, when given the choice, to use proportion variables as opposed to their equivalent absolute values? So at first sight, these are completely unrelated questions. They come from very different domains. They're both applied and methodological. But they do have one thing in common, and this is that they all relate to examples of compositional data. And recognizing this can help us understand the challenges better and solve many of the issues that we might have. So the first section that I'm going to cover is what is compositional data. And one way to define this type of data is that this represents any type of data where we have different components or parts that together sum up to a meaningful whole or total. For example, I mentioned nutrition already. Total energy intake can be understood as the sum of energy from different energy sources like protein, carbohydrate, and fat. Similarly, if we're working with population, one way in which we can break down the total population is in groups of according to age or anything else that might be meaningful in our analysis. Similarly, we can think of time spent doing different activities. For example, the time that we spend physically active, sedentary, or asleep adds up to the total hours that we have available in a day. And there are many other examples. Commonly, this is understood. Microbiome is often understood as compositional data. Geology, I think someone mentioned in the audience before we started, and that's where a lot of the field developed. And if you think about it, almost all data can be conceptualized as compositional because we can take any concept and break it down into further components. But when we typically refer to data as being compositional, is when there is a specific interest in analyzing the compositional components, either in relation to each other or in some way in relation to the whole or the total. And in this talk, I'll use some existing suggested notation for depicting compositional data in DAGs that I'm not going to introduce in detail, but if you are interested and often work with compositional data or other deterministic relationships, there's this useful video by Peter Tennant who introduces it, and there are publications out there. But very briefly, the way we would depict diagrammatically compositional data, we can use this example. Suppose we have, in a very simple example, just two variables, x1 and x2, that together sum up to xn. So x1 plus x2 equals xn, very simple. And we have some example outcome of interest, which is y. And if you're already familiar with DAGs, the only important thing to note that is different in how we would depict it in compositional data is that we tend to use double arrows to represent deterministic relationships because this sort of sum is not a probabilistic but a deterministic relationship, and DAGs are designed to be probabilistic. So if we have this very simple scenario, one common challenge in this context is if we were interested in the effect of one of the compositional components, so x1, on the outcome y, should we condition or adjust for the total, or xn? And this is a really important, it sounds simple, but it's a really important challenge because it has big implications. As soon as we condition on the total, or xn in this case, this would create a dependency between the compositional components x1 and x2. In other words, we can think of adjusting for the total as keeping the levels of the total fixed. So in these cases, because x1 and x2 are the compositional components, as one increases, the other one has to decrease because we fixed the total. If you're familiar with collider bias, and I know that the previous BEMC talk was on collider bias, so if you haven't watched it, you should maybe catch up. But this is very similar to a collider bias structure. We have some sort of downstream variable. The way we condition on it, this creates a dependency between earlier parent variables. However, uniquely in the context of compositional data, this sort of dependency between the components can actually provide meaningful results. And what this means is that in compositional data, we can actually estimate two main types of effect. The first one, or the collider biased effect, we call the average substitution causal effect. This is the effect on the outcome of increasing one compositional component while at the same time decreasing another compositional component to keep the total fixed. We can also have and estimate another type of effect, the average additive causal effect. This would be the effect of increasing one component x1, and therefore, as a result, increasing the total as well. So this happens when we don't condition on the total. We allow it to vary. Therefore, if we want to estimate the effect of increasing one of the components, the total would automatically increase as a result. And a few more things on compositional data before we cover some of the actual challenges. I mentioned earlier that compositional data can be of two main types with variable totals and fixed totals. Dietary data is one of the most commonly I guess, used types of compositional data with the variable total. And because of my background in nutrition that Jess mentioned, a lot of the examples that I'll be using today come from nutrition or nutritional epidemiology, a lot of the methodological challenges. But an example here is total energy intake. That's the sum of the different energy contributing components. And this total can vary. So we can have different total energy intake values for the day between people, but also within people on a daily basis. These can change. And we know that when we adjust for total energy intake, for example, in a model, we're estimating a substitution between these components. But we can also have data that has fixed totals. Most commonly, this is seen in anything to do with time or time use or some sort of time constraint. For example, different behaviors that we can participate in during the day sum up to the total time that we have available in a day. The total here can never vary because it's always 24 hours. So for the total time in a day. So whenever we have compositional data with fixed totals, we can only estimate a substitution effect because this total is conditioned on by nature. So it's not possible to estimate the effect of, for example, increasing the time we spend physically active and as a result, increasing the total time we have in a day. That's not possible. Right, so now we know that there's these two types of compositional data, and we know generally that when we condition on the total, when we adjust for it, we can change the interpretation of what we're estimating. So if we actually have compositional data and want to consider some sort of adjustment for paths or the total, the compositional total, we can consider what adjustment approach to use. And I'm going to use the field of nutritional epidemiology to demonstrate some of the main approaches. And specifically nutrition, total energy intake historically has been, adjustment for it has been recommended for many reasons. One of them is to allow for comparisons within similar levels of energy intake so that we estimate the effect of some food and not necessarily the effect of just eating, consuming more. But also to adjust for some unobserved determinants of dietary intake and composition that we know might exist, but there's no way to measure them, such as metabolic efficiency, or maybe they're measured, but we don't have a good measure. And it's believed that total energy intake can offer a good proxy for many of these things. And there are other reasons, and this has been discussed a lot in the literature. And for this, I'm going to use a slightly extended example where we have 7 components just for illustrative purposes. We have sugar, starches, fiber, saturated and unsaturated fat, protein, and alcohol. And these add up to total energy intake. We have an example outcome, which is fasting plasma glucose. And here we've also depicted these unobserved determinants of dietary intake and composition that we hope the observed dietary variables capture, at least to some extent. And we said that in these cases, when total energy intake adjustment is recommended, we have to remember that as soon as we do that, if you want to estimate, for example, the effect of increasing sugars in the diet, but we've adjusted for total energy, we're estimating the effect of increasing sugars and at the same time decreasing a combination of the other dietary components. So what do we do if we don't want to create this substitution? The most sort of straightforward way is to actually remove the exposure from the compositional set. In other words, we can adjust for the remaining energy intake because now the exposure is not part of it. It's not part of the compositional data in the same way. So we can estimate the effect of increasing sugars while still adjusting for the rest of the diet without estimating a substitution effect. And in terms of the models that are being used, so I'll just go through the main types in a very simplified form. The standard model simply involves conditioning on total energy intake once we've specified the exposure in the model. And we said that this is a substitution. There's another model which is known as the residual model, which kind of achieves the same, but using an additional step where we first regress the exposure on total energy, and then in the second stage of the model, we use the residual, and this is mathematically equivalent, and again is a substitution model. The other approach that I mentioned, we can adjust for the remaining energy or the remaining compositional set, which will not be a substitution. So this is if you want to estimate an additive effect. We can also do the same, but where remaining energy is broken down into different components. Not a substitution again. And finally, we can do what's known in nutrition as the nutrient density model, but in more general terms is when we add the total as a denominator. And we can additionally adjust or not for the total as a separate term, which ultimately we are estimating a form of substitution again. So what we want to do is try and figure out whether all of these models, we knew already that they were answering different sort of questions, and some of them are substitution and others are not. We wanted to see whether they were equally, they performed equally well for one of the main reasons behind adjusting for the total, which is to try and capture some of that unobserved confounding that we've got. So we use this DAG as the data generating process for the simulations. We simulated these 7 dietary components, both in context with and without confounding. And then the total energy and remaining energy intake were calculated. They were deterministically derived rather than simulated separately. And we conducted 100,000 simulations, and we simulated some true effects that we could then compare the results of the models to. And I'm not going to go into more detail on specifically the simulation process, but these are the main kind of important things to bear in mind. And rather than going through each separate results, I'm just going to try and focus on the main messages of this work. And the first message is that, as expected, we demonstrated that retaining more of the individual compositional components allows for better adjustment for confounding. So this shouldn't be surprising because we're keeping a lot more of the variation to work with in the model. But often these two models, for example, here we have the situation where we adjust for the remaining energy because we don't want a substitution. Often these are considered as essentially equivalent. So why would we model all these components separately if we can just add them together as a remaining energy variable? However, as soon as there's any confounding, and there was nothing else in the simulation, no selection nodes, no other confounding. Essentially, combining these components into one wasn't enough to remove the confounding. And this was the same in the other scenario where we had total energy. So we had a substitution model. We can still derive this substitution effect from a model that contains all components. But again, having total energy as a single variable wasn't as effective as all of the components. And the second message is that really, we should really think twice before using ratio variables. And there's a lot of literature on ratio variables in general, but specifically in the context of compositional data. And I'm going to come back to ratio variables at the end of the lecture. But in terms of the nutrient density models, we had a true estimate that we wanted to compare to, and we can see that for the simple nutrient density model, even when there was no confounding, so there's nothing in the data to basically lead to a biased estimate, even then the model didn't perform quite well, but this was improved when we added total energy as an additional variable. And you might notice that we've got these question marks for the effect. And this is because models with ratio variables don't really target meaningful and interpretable causal effect estimates. And a lot of people are rightly unconvinced when we sometimes say this, but actually there's a lot of history and literature on this topic. And as I said, I'll come back to this towards the end. Right, so we now covered these different approaches that people might use when they've got compositional data, using some of the examples from nutrition. And we also mentioned that often, we might adjust for total energy, but not realize that this creates a substitution, and maybe we don't want a substitution. But equally, we must consider what if we were specifically interested in a substitution effect, because this is an equally meaningful question to ask in many domains in compositional data. In fact, again, to use the nutrition context as an example, a lot of dietary guidelines often recommend substituting certain foods or nutrients for others. For example, all of you have heard the recommendation to replace saturated fats with unsaturated fats, for example. And when we have experimental studies, it's very straightforward to think about how we might design a study to estimate the effect of substituting certain foods. But in observational data, we have to somehow find a way to estimate the substitution from data where people never substituted anything. So we try to use some sort of statistical approach to do this. And before I continue to the actual approaches, I'll just briefly go back to the DAG that we were looking at. So suppose originally we might have been interested in fat as the exposure, just illustratively, and the fasting plasma glucose as the outcome. And we said once we condition on total energy intake in such data, we would be estimating the effect of fat instead of protein and carbohydrate. But we can also additionally condition on other variables, for example, protein. So we've now conditioned on total energy, we've now conditioned on protein, so we've conditioned on another compositional component. What we're estimating in this example is the effect of fat instead of carbohydrate. So the effect of one compositional component instead of the one that we haven't conditioned on, because that's the only other one that can vary. So this is how we can estimate very specific substitutions when we've got compositional data. And we'll use a slightly extended example, again with fat, carbs, and protein, but where we have two types of fat, saturated and unsaturated. And suppose we're interested in replacing saturated fat with unsaturated fat. We can specify the model in a few different ways. One of the most common approaches is known as the leave one out, where we adjust for total energy and all compositional components except one, which is where the name comes from. For example, here we've got saturated fat, and we've also adjusted for total energy, protein, and carbs. So the coefficient for saturated fat will represent the effect of substituting saturated for unsaturated fat, because that's the one that we haven't conditioned on in the model. So we're leaving one out. We can also use what's known as the energy partition model, where essentially this can be specified in a few different ways, but one of those ways is that we have the two components that we want to substitute in the model, saturated and unsaturated fat, and then we condition on the rest of the diet, for example, through remaining energy. The substitution effect in this case would be estimated as the difference in the beta coefficients between the compositional components, and we can do that because we have compositional data. And again, we can specify the same model, but while breaking down the remaining energy into the specific components. We've discussed that this might often be the preferred approach. But there are other variations and extensions of these models depending on the exact question. For example, we might decide to keep condition on the total protein, for example, and substitute between sources of protein. So you can see how these can be very, can be tweaked to make them really targeted to our such question, and they're used for both macronutrients and foods. And the most important thing, the first thing we need to always think about when interested in substitutions in any type of compositional data that we might be working with, is that ideally these substitution effects that we are targeting should be well defined. So ideally, we would be estimating the effect of substituting one component for one other. For example, if, say, we were interested in the substitution effect of meat instead of fish on the same glucose outcome, and we adjust for all other foods, this might either take the form of a leave one out model, where we leave fish out, or another model where we look at the difference in the beta coefficients between the two compositional components. And when we have a scenario like this, where the model and the research question is well defined, both of these models will be identical mathematically and will produce the same estimate, regardless of whether we have macronutrients or foods. As you might expect, in reality, substitutions, both the models and the research questions, are often not well defined and might often include multiple components. So we're estimating something that is an imperfect average. And so it is not as easy to interpret what this is. To take the other extreme, where rather than just substituting one for one, say we estimate the effect of meat instead of every other food on average. This is the other extreme that we can think of. For example, we either leave everything else out of the model in the leave one out case, or we specify a really simplified model where we look at the difference between the effects of meat and all the remaining food or all the remaining compositional components. But because in both cases, we've collapsed all of the foods or all of the components into a single variable, what would happen is we would end up with a really distorted effect. This makes it first really difficult to interpret because the summary or the composite variable essentially would be a variance-weighted effect. And this makes it really difficult. The effect will not be transportable because it will be really specific to the variances in the data set you're working with. So first, it wouldn't be transportable to other populations, but probably wouldn't be transportable to even any other data sets of the same population. And one caveat here is that we mention in both adjustment and substitutions that ideally we should try and model all of the compositional components, which in theory will have challenges. But we ideally want to do this because we would be able to retain more information, which helps with having a substitution that's well defined. But it might not be realistic. We might have too many compositional components. We might have small sample size too small to add more and more variables, or we can have a multi-collinearity problem. And the potential solution to most of these challenges is to actually combine variables where relevant. For example, variables that are highly correlated already explain the same variation. They carry the same information. We don't, of course, need both of them in the model. They can be collapsed. Or variables that convey the same information relative to the outcome. For example, we wouldn't have to specify each type of vegetable, but if this is really relevant to the outcome, then maybe we do that and combine other variables. It's very context specific. Perhaps an even bigger problem, and mostly this is an issue of, for example, when appraising the literature or reading papers, because once you understand compositional data, it's really easy not to do that, is what we call inadvertent substitutions. Suppose you're reading a paper and the author seeks to estimate the effect of meat on systolic blood pressure. And they decide to adjust for total energy intake, fruit and vegetables, for example, as these are potential confounders. So the model might look like this: we have meat, the exposure, total energy, fruit and vegetables. So the researchers might not recognize that first they have adjusted for the total energy, and this has created a substitution. But second, that this has created a substitution with all of the components that are not adjusted in the model. So rather than what the original aim might be to simply estimate the average causal effect of meat, what we end up with is the substitution effect of meat instead of everything that's not fruits and vegetables. And often we would find that this is nothing to do with the original research questions that researchers might have had. And depending on exactly what is being substituted with what, the coefficients can have completely different values. They might have completely different directions. So it's really important to not create substitutions when we don't mean to create substitutions. And the final important point in substitutions in compositional data is to think carefully about the units of analysis, the units of the variable, sorry. One thing you can often come across in substitution models is mixing the units. For example, in the context of nutrition, this might be specifying some variables in calories, others in grams, and so on. And suppose we have this simple scenario where total energy intake is just the sum of calories coming from 3 different foods and nothing else: food 1, food 2, and food 3. And suppose we create otherwise a well-specified leave one out model where we have the exposure, we condition on the total, and then we only leave one out. So we estimate the effect of food 1 instead of food 2 in this case. But we have total energy in calories, whereas the foods are in grams. And what happens here is that 100 grams of meat will not always be the same number of calories. 100 grams of cheese, similarly, could be many different calories. And so the problem we have is that when we have different units, the data is no longer strictly compositional. And the interpretation that we would expect will not be the same as when we have compositional components with the same units. And this creates estimates that we call obscure, because it's really difficult to actually determine what the model is estimating, because that would require that we know the information on the specific energy density, the water content of these foods, which will always be different. So we can never say with certainty what the model is estimating exactly, because we break down the compositional nature of the data. And sometimes, not always, but depending on the data structure, mixing the units can lead to sign reversal. For example, in simulations we had done on this second project in my PhD, we had models where all of the variables were in calories and models where all of the variables are in grams. And these gave us essentially effect estimates in the same direction. But when we use mixed units, the estimate at the opposite sign. In otherwise, the same simulated data with the same estimated effect. So simply changing the units from the same to mixed, sign reversed. And this is not universal. It would take a specific data structure, but it's really difficult to predict what would happen, and there are no general kind of things that we can check to know how bad it is. And so the simulation, as I said, I wasn't going to go through in a lot of detail on the technical details, but they are available in this paper in the top left. But there's also a lot of other excellent literature on substitution models. And we're down to the last section. So we covered what compositional data is, what sort of things we might consider when we wonder whether we need to adjust for the total or not in the compositional data context that we've got. And then we talked about if we are actually interested in substitution effects, and how might we specify these models and what to think about. But there are other challenges and some other parametric decisions that we might think about in compositional data. And I promised that earlier that I'll come back to ratio variables. And this is because they require their own special section in this talk. And they're really important because compositional data is very, very often presented as ratios or proportions of the total. For example, percentage of energy intake that comes from fat, or percentage of our time that we spend sedentary. And it is very intuitive to do so because the compositional components are a proportion of the total. It's very meaningful to consider things in this way. And there is nothing inherently wrong in presenting the data this way or communicating anything about the data in terms of proportions. The problem arises when we use these ratios or proportions in analyses of correlation or regression. And this practice has been discouraged since the 19th century. I mentioned about the long history of people writing on the topic. But the first one that we know of to describe this issue was the statistician Kyle Pearson, and he wrote about this back in 1897. And I do recommend you read this paper. It's actually really, really interesting. But the one thing that is relevant to ratio variables here is that he described a scenario where we start with three variables that are completely independent of each other. So they just share no relationship. When we then create ratios with one of these variables being a common denominator, we would see that the ratios will have correlation between them. And on average, this would be about 0.5. So we would find that a correlation exists between the ratios, even when the variables, the original variables, were completely orthogonal. And he described this, he named this spurious organic correlation, or simply a spurious correlation. So if you've ever heard this term, this is this was the scenario where Kyle Pearson coined the term to describe the problem of ratio variables. And since then, a lot of other people have tried to explain the problems of ratio variables, but for many reasons, they are still popular in observational research. But the one thing that is really important in this context is to remember the compositional data, the totals can be variable or fixed. When they're fixed, they're constant. And because ratios involve division, whether or not it might be appropriate to use ratios in compositional data would depend on the type of compositional data. In the physical activity domain, whenever we consider different activities in terms of the time spent or anything to do with time, as I mentioned, the totals will be fixed. In these cases, the total time in a day is always 24 hours, or if we want that in minutes. So this is a constant, and dividing by a constant will rescale the effect, but it doesn't introduce any variation. So we're just rescaling, but there's no spurious correlation to appear from anywhere. However, whenever we have compositional data with variable totals, and this will be most of the cases of compositional data, ratios do introduce problems. This is because, again, to use the example of nutrition, the total is often used as a way, the division by the total is often used as a way to sort of account for it or remove the total from like the model. But division is not a valid method of adjustment, and I'm not aware of any training program in which division is taught as a adjustment method. All we're doing when we create a ratio is we're conflating the effects of the numerator and denominator in the same variable. And in more extreme cases, when the denominator is more strongly associated with the outcome than the numerator, this might lead to sign reversal of the estimate. For example, the issues with the ratio model in nutrition, the nutrient density model, these issues have been discussed in the past. This paper on the left is from probably 40 years ago now. And also the simulations that I mentioned earlier on were in our paper from a few years ago. And it's always easier to understand things using DAGs. So the final things about ratios, so I'll try and show you this animation. So suppose, again, we have the simple x1 and x2, two compositional components, and an example outcome y. Together, they sum up to xn, the compositional total. So when we create ratios from them, we might think, okay, if I represent this as a ratio, as a proportion of the total, it wouldn't matter that the total has any variation. You know, I'm accounting for the total by representing this as a proportion. But it's really easy to see in an illustrative way that when we create the ratio, we haven't removed the total. In fact, we've introduced it into the variable where it wasn't in the first place. So now any effect of these ratio variables simply represents the conflated effect of both the numerator and the denominator. And the effects will go in very unpredictable directions. It will be very data and outcome specific. And we simulated these two scenarios with fixed and variable totals and 4 components, each just for consistency. Mostly just to demonstrate what we sort of expected anyway, and this is in the context of 10,000 simulations, but whenever we used ratio variables in the context of fixed totals, essentially the true estimate that we expected was obtained on average without any problems. However, in the other example, where the total varied, that wasn't the case. So on average, from across 10,000 simulations, the average estimate was quite far away from the total, considering there's no confounding in selection nodes. And then we also tried conditioning on the total in addition to the ratios in the model. And this does offer some improvement, but again, it's not a complete solution. And how much improvement it would offer, again, would be data specific, and it's not a general sort of level of improvement that we would see. And the final consideration in the modeling of compositional data is nonlinear effects. And one of the most commonly cited criticisms of the standard substitution models is that they only handle linear effects, whereas in reality, a lot of the effects might be nonlinear. And this is true because if you think about this leave one out approach, where we condition on the total and we rely on something being out of the model such that we can calculate the substitution effect. Of course, this relies on the effects adding up in a linear way. And that is a limitation of the leave one out approach. But substitution models are regression models, which can handle nonlinear terms as long as we don't use the leave one out approach. And I'm going to use a very, very simplified, a sort of made up example with 3 components. But suppose we have one log term, we have a square term for another component. Again, this would be depending on your data. So just for illustrative purposes, since this is a model, we can, of course, translate these terms into actual beta coefficients and variables, and we can calculate the value of the outcome under these specific conditions. What we can then do is, for example, say if this one component was 400 instead of 500 and another one was 100 more, so we create the substitution in this way, we can then calculate the value of the outcome under a different scenario. So this is only possible, again, if we use all compositional components. So it's sort of another reason why it's good to consider this, because otherwise we wouldn't be able to model nonlinear effects in this way. And finally, just to really nail the point, we talked about well-defined substitutions, and specifically that we have to consider what the substitution is, for example, ideally one component instead of one other. But when designing research questions with compositional data, it's also really important to consider things like, what is the size of substitution? Are we interested in substituting different? My microphone is escaping. Sorry, is that okay? Yeah. For example, if it's different activity behaviors, are we interested in substituting 1 minute or 1 hour? This would be very different scenario. Also, what are the starting values that we want to substitute from, and are they meaningful? If we want to estimate the effect of decreasing some food or some activity, for example, but they're already quite low in our data, then are we estimating something that's possible and that's meaningful? And these are, of course, very important for a meaningful result in meaningful research question. But when we start thinking about, say, we might have nonlinear effects, they might determine the specific parametric shape, because that might differ depending on the specific research question. And so it's good to be very as specific as possible. Even this might not be ideal, but for example, we might be interested in estimating the average substitution effect of increasing fish intake from 50 to 75 grams, while decreasing red meat intake from 100 to 75 grams, while keeping the rest of the diet unchanged on systolic blood pressure in German adults aged 40 to 60 years. So it's good to be as pedantic as possible about these things, because this is where you get the most meaningful results. Some of you might see this as very naturally suited to the target trial framework. And there's this really nice editorial on mapping some of the existing adjustment approaches to hypothetical target trials, again, specifically in the nutrition context. And I'll finish with some general summary of the sort of 3 sections that I covered. First, in compositional data, when we are considering adjustment or not for the total, first we need to remember whenever we adjust for a compositional total, regardless of what that is, this would always invoke a substitution. An adjustment should be informed by whether our research question involves a substitution or not. In other words, by the causal estimand of interest. And something that I haven't got here, maybe I should have, is to remember that when we have fixed data, fixed totals, this total is conditioned on by design, by nature. So we always have to keep this in mind. We have no choice. And we also found that whenever we're faced with the choice of different adjustment approaches, the ones that involve modeling as many compositional components as is practically possible in our case would offer better adjustment for confounding, which is one of the reasons why we might consider adjustment. Moving on to substitutions, when this is of interest, these should be as well defined as possible and should consider the specific contrast between components, the size of the substitution, and the starting point. Ideally, where possible, we should use the same units for all components, because otherwise we are breaking down the compositional nature of the data and the interpretations that we rely on might not be possible. Again, another reason to try and model all components is that this makes it much easier to ensure that the substitutions are well defined and we're not combining things into like one variable, when that might create issues. Ratio variables, they're not just best treated with caution, I would say are best avoided in compositional data with variable totals. But when the compositional total is a constant, then we are simply rescaling the effect and we're not running into any of the same issues. We should consider the parametric shape of the relationship. This is often neglected, specifically the nutrition context, and I'm not so familiar with other the literature of other compositional contexts. But one of the reasons why it is neglected is because a lot of the models that have been historically used rely on the effects being linear. So it's not really a criticism of practices, but mostly the methods that, it's a limitation of the methods that have been used. But again, if we don't rely on, say, a leave one out approach, but we model our components individually, we can actually estimate nonlinear effects in a more straightforward way. And this, so many people have talked over the years, and I've learned and I've changed my opinion, you know, even a little bit after speaking to like amazing colleagues around the world. But I wanted to specifically acknowledge the co-authors on both the 2 papers that I mentioned and the 3rd final paper that is still in its peer review journey. And I want to acknowledge funding from the Alan Turing Institute for my PhD. And that's all from me today.